Buddy. What I want to do here first is to just kind of run through the quiz questions. In my opinion, every single one of these would have been a no calculator question. Now, obviously, I didn't require that from you guys. Eventually, we will do some of those practices without calculator, but not the first time. But I just want to kind of talk through how you go about approaching doing some of these without a calculator, and just kind of how that, like what you should be thinking about and all that. Okay? So the first one says the graph of the function f is shown above, which the following statements is false. Well, f is continuous at a, and you can see right away it's not, right? There's nothing to do there. Should have been very straightforward right away. So it says FGH, or let FGH be the functions defined here. Assuming that x is not 0, all the following inequalities are true on the interval from -1 to 1 for x not equal to 0. Which inequalities can be used with the squeeze theorem to find the limit of the function of x as it approaches 0? So I am going to be concentrating on what's in the middle. So here is my f of x. Well, when at its minimum, as x approaches 0, this is undefined or whatever, but the maximum value this could have would be when sine is at pi over 2, which where it's at +1. So that would be like 1 over pi, which is bigger than 1/4, but this could be -1 over pi also, which is certainly smaller than that. So the fact that this doesn't have any negative on it, I'm kind of out on that. G of 8 or G of x looks just like a classical squeeze theorem situation where I know cosine is bounded between -1 and +1, and then we multiplied both sides of that by the x to the 4th. So right away I'm like, yes, that looks lovely to me. The last one that I have to check is 3, and that looks like it's set up the way I would expect it to. The problem is that I remember that tangent is bounded between -infinity and +infinity. Its range is. These are all trig things from last year, right? So right away, I'm real suspicious that this is not going to go. And indeed, it won't work. Again, if you think about it at like tan of like pi over 4, which is where cosine is at 1, that would give me just pi over 4 squared, which is way bigger than, thank you, than that. Sienna, for you. You're welcome. So B looks like our best option here. So it says the limit as x approaches a of f of x is equal to L, where L is a real number. Which of the following must be true? Well, this is like can I draw a function f where the limit exists, but this isn't true? So like if a is here, I could draw that, the limit exists, but f of a doesn't. F of x is continuous at x equals a. Well, that same example, clearly the limit exists, but we don't have continuity. F of x is defined at a. Well, same example I drew doesn't have that. And then the last one, that f of a has to equal L. Again, the example that I drew doesn't have to have that. So should answer none. Which of the following is continuous at 1? This is a lovely use of our continuity theorems that we just looked at. So if you remember the following theorems, so all exponential and logarithmic functions are continuous on their domains. So is 1 in the domain of the natural log of x? Sure, the natural log of x, or natural log of 1 is 0. That's defined, so clearly this one is continuous. E to the first, well, exponential functions are continuous over all real numbers. Their domain is all real numbers, so that one's fine. And then the last piece, the composition, I know that, again, the composition of two continuous functions is continuous as long as you're working on the domain. So e to the first minus 1 is positive number, so I can take the natural log of that. So 1 is in the domain of that composition, so they're all continuous at 1. I didn't do any proof. I didn't have to look at my calculator. I didn't have to draw any graphs. I just used what I knew about continuous functions. Again, quite a powerful theorem, allows you to do quite a bit without having to do much at all. Says if the function f is continuous for all real numbers, and if f of x is equal to yada yada yada, where x, and then when x is not equal to -2, and then f of -2 would have to be. So again, this should look like a removable discontinuity thing that you would have remembered from your Algebra 2 class. So we would say that this just simplifies down to x minus 2 as long as x isn't equal to -2. So we'd have, like, if I graph this, you'd have something like this, right? What we want is the value to fill in here, which is just what I would get if I plugged in -2 for x. Just figuring out where the hole is on that removal, where the hole is from the removable discontinuity and filling it. That's all we're doing. Does that feel okay? Again, nothing that we've done so far would be something that really requires a calculator. Our next one here, the limit as x approaches 2 of x squared plus x minus 6 over x squared minus 4. If I tried plugging 2 in, I'm going to get 0 over 0. However, I should recognize that that is factorable, that rational function. So those can reduce. So this is the same thing as just taking the limit as x approaches 2 of x plus 3 over x plus 2. And then you can just direct sub to get 5 over 4. Everybody cool? The next one says, which of the following limits are equal to -1? So this one, again, here I would probably, this piece screams, please factor me and reduce. Oh, yeah. So this, we have the limit as x approaches 3 of negative x plus 4. Direct substitution, that gives me 1. So that one's out immediately. The next two I have to think about a little bit. Here, if I do direct substitution, just plug 0 in, I'm going to get 0 over 0, correct? But since I know x is approaching 0 from the left, that absolute value of x is really going to be like negative x. Right? Remember the definition of the absolute value? Right? That's the piecewise definition for absolute value. So if I think about it that way, it can just reduce down to negative 1. Or you could think about it as like, okay, that's really the x over x, but I'm going to be plugging in negative numbers. So the absolute value is going to nuke the negative on top, but it's going to leave the negative on bottom. So it's going to be like, you know, x over negative x or whatever. So that one certainly looks good. And then this one is one of these limits at infinity that we looked at before. And here we just need to look at the leading coefficients. So the leading coefficient from the numerator is negative 1. The leading coefficient from the denominator is positive 1. Since the degrees of my polynomials are the same, I can just look at leading coefficient over leading coefficient. And that should be negative 1 also. Everybody okay? Am I going too fast? This is all right? Okay. So again, here's another limit. If you try doing this by substitution, you're going to get 0 over 0. So again, there's going to be some clever factoring that we're going to do here. So the way I would think about it is, okay, I do my difference of two squares factoring. And this is also, I'm going to think about as a difference of two squares. How sneaky is that? You could have also multiplied by the conjugate. That would be okay also. And then when we do the limit, we can just now do direct substitution. You'd have gotten the same thing if you had multiplied by the conjugate also. I think I saw people doing that pretty frequently. But you could also think about it as a factoring. Either way is fine. The next one, it gives us a piecewise function, but the second piece has a extra variable in it, and they're asking us, okay, for us this piecewise function to be continuous, specifically at the boundary between the two pieces, what does that value of k have to be? Well, what we're really drawing here is like, you know, I got some, there's my first piece of some quadratic, and then I want to pick the k so that my next piece, you know, attaches right over the end. So the way to do this is to just plug in and figure out what this endpoint is in red. So I know that's 3 comma, and when I plug in 3, I get 9 plus 2. So this is the point 3 comma 11. So then if I take this piece and I plug in 3, I have 18 plus k has to equal 11. So k just has to be negative 7. Everybody's okay with that? The last one, it says if the function is, if g is the function defined by yada yada yada, what is the limit as x approaches pi over 4? As soon as I see this, I'm thinking unit circle. So this is, again, something that could conceivably be done without the graphing calculator. Does the AP believe that you should know the unit circle measurements or the unit circle values for sine and cosine? Yup. All right. So the easiest way to do this, I think, is to use some trig identities. So the trick that I'm going to use is I'm going to replace 1 with cosine squared plus sine squared. And if I simplify the denominator, that's going to give me a cosine squared minus sine squared. Which that denominator can factor. Oops. So what I simplify this down to is I have the limit as x approaches pi over 4 of 1 over cosine x plus sine x. Now I can do this by direct substitution. It's lovely that they gave me pi over 4. That's the same as 45 degrees, so sine and cosine are both the same thing. I'm going to write them as 1 over root 2's instead of root 2 over 2. Just because it means that there's no reducing later on. So that's 2 root 2's, and if I make the reciprocal, I get this, and that could reduce down to just 1 over root 2, which I think is what the answer was. Yep. 2 is the same thing as root 2 times root 2. So you can reduce. Just to demonstrate to you that all these problems are realistically doable without the graphing calculator. At no point did I use anything that you hadn't seen before. Now, did I have to rely on past stuff that's like, ooh, I don't know the unit circle that well right now? Yeah, probably. Is that something that we'll want to make sure that we're fresh and up to date on before like our AP exam, if you're not really good with your unit circle or some of your basic trig identities? Yeah, but notice the only trig identity I used in that was just 1 is equal to sine squared plus cosine squared, which I'm betting that all of us remembered that one. Now, to think to use it there may be a different story, but all of that was doable with no calculator. And my opinion was that I think that all of those would have been no calculator questions. I forget what I have to look at to tell on the question. I think if it had the calculator by it, it meant you could use the calculator on it. I don't think any of those had the calculator by them. But it's neither here nor there, right? It was fine that you guys used it. Oh, yeah, of course.
So how did cosine square x plus sine square x sine square x have plus 1?
So I have 1 sine squared minus 2 sine squareds. Gives me negative 1 sine squareds. Yeah, no problem. All right. Let's start a new page here. And boy, that is teeny tiny up there, huh? We'll start with questions from homeworks if anybody has anything. Mackenzie? 2.5, number 4, you said? Okay. Well, let's do this. So this one involves looking at a graph. I'm going to try to snip that in here real quick. All right. It says, from the graph of G, state the intervals on which G is continuous. So, right here, we're continuous. So I would say we're continuous from the right all the way to -2. And then -2 up to +2. Notice that those are both empty, so I wouldn't include those. 4 appears to be an asymptote, but we have a filled in endpoint there, so that's continuous from the right, or from the right. So I'd assume they want that. And then the other end with the asymptote, notice we're empty at that end. And then our last one would be 6 to 8. Does that feel okay, Mackenzie? Victoria. 8? Sure. 8 says to sketch the graph of a function as continuous except for the stated discontinuity. It says neither left nor right continuous at -2, continuous only from the left at 2. Okay. So I'll make this -2. I'll make that +2. Continuous only from the left at 2 means that it's going to have like a closed, and then we're going to be going this way something, right? I just need to decide what I want to do at 2. So I think, or -2, excuse me. One way you could do that is you could use like a vertical asymptote. There the function is continuous everywhere except at -2. And it's not at -2, it's neither continuous from the left nor the right. And it is left continuous at +2. And I guess it says I'd have to do that to make it continuous everywhere else, right? Victoria, is that okay?
Yeah, I just don't understand. Why did you go last?
Well, it says that the function should be continuous everywhere except for the stated discontinuity. So I needed to continue making it continuous past 2, just to follow the directions.
Okay. So it would need to be like those asymptotes that would make it not continuous to the left, or -2 to the left or right.
Correct. Because it's not defined at -2. on either the left or the right. You could have also done, instead of doing an asymptote there, you could have done like something like that. That would be okay.
Because like it's open.
Correct.
Okay, but it's defined at -2.
It is defined at -2. You don't necessarily need to put that point in there, but
Okay. Okay.
you could do it that way also. That would be okay.
Okay.
Does that feel okay?
Yes.
All right. Nico,
Can you do 49 on
2.5, number 49. Sure. It says, this was 8, I think. 49 says, if f of x is equal to x squared plus 10 sine x, show that there's a number c such that f of c is equal to 1,000. So I would use the intermediate value theorem to do this. All I want to do is show that I can find some x that gives me that f of that. I want to find x's a and b such that f of a is less than 1,000 and f of b is greater than 1,000. Since I know that this is continuous all the way through because I have the sum of two continuous functions. So the first thing to use the intermediate value theorem is I have to have a continuous function. So I'm just going to take a moment to state why I know that f of x is continuous. Again, on the AP, if they doing a problem like this, they would, if you didn't show that or state why f of x is continuous, you would not get full marks for it. That's definitively part of the theorem, and it's an easy part to overlook, but you need to like write it down. So I'll start with f of 0 because that's really easy to see that to 0. And then if I do like f of 10,000, that's, I don't know what it is, but it's going to be greater than 1,000, right? That may be a tad of overkill. Let's do f of 100. That should be enough even. But it really doesn't matter what we get here. So this is 9994, yada, yada, yada. So since f of 0 is less than or equal to 1,000, which is less than or equal to f of 100, by the intermediate value theorem, there exists c on the interval from 0 to 100 such that f of c equals 1,000.
Thank you.
Yep. So just an application for that intermediate value theorem. It doesn't actually ask you to find the c, just need to show that it exists. Yep. So whenever you have like show something exists, you're probably using a theorem to show the existence of it. You don't actually need to find it. Because that's, well, I guess it's not really that bad in this case, but you'd have to use your calculator. I don't know of a good way to get the exact value of that to come tumbling out. Others. Mia, is that a hand? Same section? Okay. Okay. It says, prove that the equation has at least one real root. Okay. So I would start by rearranging it to look like this. Yes.
So do we want it to, like, do we want it to make it equal to 0?
Yeah, because I'm going to say then I'm going to call this function my f of x.
Okay. Like, even on the ones that's like 51 through 54, we want it to make it equal to 0.
Mm-hmm.
Okay.
Yeah, because I'm going to use the intermediate value theorem for this, so I need a function, and that function needs everything all on one side. So again, first thing I'm going to do is state why I know this function is continuous. It's the sum of two continuous functions, a polynomial and a trig. So now all I need to do is find some value of x that gives me a negative output and a value of x that gives me a positive output. That would be enough. So let's say, let's see what negative f of negative 1 is. I think that's probably enough. Yep. Whatever, yada, yada, yada. And now I just need a value that gives me a positive output. I think that 1 will probably do it. Yep. Yada, yada, yada. All right. Since f of negative 1 is less than or equal to 0, which is less than or equal to f of 1, by the intermediate value theorem, there exists c on the interval from negative 1 to 1 such that f of c is equal to 0. Mackenzie. Yeah, if f of 0 gives you a negative value, yeah, absolutely. You just need something that gives you a negative and something that gives you a positive. Any x is fine that does that. I mean, if it was x negative 7,000 and x positive 7,000, that's fine. Like, it's a hassle to find the 0. I mean, obviously, if you're like actually looking for the 0, you want that interval as small as you can get. But it doesn't matter for this question. If all you need to do is show existence, then just show existence.
So you just want to find a negative and a positive and then intermediate.
Yeah, if you're looking for the 0 to show a 0 exists, yeah, that's all you need to do. Mackenzie? Okay. Mia, you're happy though? Okay, go ahead, Mackenzie. Same section? Okay. Here it says, explain using theorems 4, 5, 7, and 9 why the function is continuous at every number in its domain, and then state the domain. Okay? So q of x is equal to cube root of x minus 2 over x cubed minus 2. Okay. All right. I'll start. This is the numerator is a root function. So by theorem 7, I know that it's continuous. The denominator is a polynomial function. Also by theorem 7, I know that that's continuous. Actually, so I have, let's say f of x, this, is continuous, right? And then if I have how do I want to do this? This is fine. What I'm doing is fine. Let's not do that. That's fine. Okay? It's polynomial. Yep. So again, that's included in 7. And then what do I want to say here? So those are both continuous. Both those parts are continuous. And this thing then is like the composition of two, so this is like the composition of two continuous functions. So we have f of x, that, and then my other continuous function is what do I need to do here? Yeah, just struggling to come up with the composition here that it needs. Let's see what the answers, what they did. But that's the idea, Mackenzie, right? You asked about this one?
Yeah.
Oh, the domain? Well, since this is a rational function, the only place that we have an issue is where the denominators equal to 0. So it's going to just be the cube root of 2 is the issue. So your domain would be negative infinity to cube root 2 union.
Negative 3 and then the cube root of 2.
That doesn't seem right. I don't know. Let's look at my solutions manual here. Are we of the mind that that was the answer that was stated? Okay. The solutions manual has the domain that I was given, or that I gave. Oh, look, theorem 4 was what I needed. That's why the quotient of two continuous functions is continuous. That's what I wanted. I didn't want to do a composition there. That's why the composition was so hard, because I shouldn't have been trying to do a composition. Right? We have two continuous things that are being divided. That's continuous, provided that the denominator is not equal to 0. That's what theorem 4. That's part of theorem 4. That the sum, difference, product, and quotient of continuous functions are all continuous over their domains.
Okay, so where's the number 3? Or is it not?
There's no 3.
Okay.
That's a typo if that's in the back of the book.
Yeah.
The domain that I wrote down is in the solutions manual, and I'm quite confident that that was correct. So my solutions manual has that solution. I don't know if that's a typo or what that was. My apologies if that's the case, Mackenzie. All right. Anybody else with questions?
Oh, yeah.
Okay, Victoria?
Yeah, can you do 43?
43.
Yeah.
Says find the numbers at which f is discontinuous. At which of these numbers is f continuous from the right and from the left, or neither, and then sketch the graph of f of x. Okay. So first thing I'm going to notice right away is that x plus 2 e to the x and 2 minus x are continuous over their entire domains, right? Each of which, since they're linear, exponential, and linear function, their domain is all real numbers. So the only places that this function could be discontinuous at is 0 and 1, which are the boundaries between the functions. Are you okay with that, Victoria? Okay. So if I do x equals 0, I'd get 2 and 1 here. So that's a discontinuity, right? From the first piece to the second piece, when I plug 0 in, the boundary value, their y-coordinates are different. That's going to be a discontinuity. Cool with that?
Yeah.
And then we'll do the same thing down here. So if I plug 1 into the middle function, I get e. And when I plug 1 into the bottom function, I get 1. So that's also discontinuous at 1. And if I sketch the graph of this, I'm going to see that we have continuity at 0 from the right and 1 from the left, but that's it. All right. So let's see. Do this. 1, 2, 1, 2, and then 1, 2, 1, 2. That's enough. All right. So I have here, let's see, I have negative 2, 0, and then 0, 2. So that's the left, or the first piece of my interval. Then I have 0, 1, and then e, which is like 2.7-ish. And then here we have 1, 1, and then 2, 0. So that's going to be what our piecewise function looks like. Does that feel okay?
Yeah, so should I just like put those 3 in the y calculator and then do like the interval and that's
I mean, what I did is I just made like an XY table. So for like y equals x plus 2, I picked negative 2, which gave me 0, and then I did 0, 2. I needed to make sure I used 0 as one of them because it was one of the boundaries. And then y equals e to the x, I did 0 and 1, which gave me 1 and e. And again, I had to use 0 and 1 because those are the boundaries. And then the last one, y equals 2 minus x, made my xy table, had to use 1, and then the other value I used was 2. And I had to use 1 because it was one of the boundary values. But that's all I did. I wouldn't even bother typing this in the calculator because you can't like control the domain of a piece with your calculator. Oh, because of the
If it's,
or equal to.
that's
Yeah, or the strict less than or strict greater than. The inequalities are telling me whether it's open or closed. If it's strict greater than or strict less than, it's open. If it's or equal to, then they're closed. So we have discontinuities at 0 and 1, but we have that 0 is continuous from the right and 1 is continuous from the left. Sure thing. All righty. Let's pick up where we left off last time. And where did we leave off last time? Didn't finish 2.6? Great. Thank you. Yes, sir.
Do we have a task plan to do the next thing?
Well, I still have to finish 2.6. I have to do 2.7. I have to do 2.8. Will the book chapter review? I don't know. I haven't gotten that far yet. I've just gotten notes written out for myself to 2.8, and I'm
So approximately, is that like 5 classes, 3 classes?
not counting today. I would think 3 to do that. Those 2 sections. Ideally, I'll finish 2.6 today. All right. So what we were doing in 2.6 is we've been looking for like horizontal and vertical asymptotes. Oh, we did this one already?
No, like what we did is we got to the limit of x approaches infinity and further than 2x squared plus 1 over 3x minus 5, and we didn't work it out.
Oh, yeah, that was what I was writing down. Okay. Yeah. So we have some function. We're looking for the horizontal and vertical asymptotes for this. That's a negative infinity there, because we have to do both ends for the horizontals. Everybody okay with what I've written here? That's how I'm going to check for my horizontal asymptotes. And what I'm going to do is I'm going to do this just using the degrees. What's the degree in the numerator? No. 1. Why is it 1 and not 2? Because the square root's on top of it. So it's really degree 1 in the numerator. What's the degree in the denominator? 1. So this is the same degree, numerator over denominator. So how do I...
Wait, can you explain again why it's not 2?
Because of the square root sign
Oh.
over top of it. That's okay. So all I'm going to do is take the leading coefficient of the numerator over the leading coefficient of the denominator. Done. Really, Mr. Kulik? Yeah, homie. That's it.
And that's just to find the horizontal asymptote.
Mm-hmm. Yep. If I want the vertical asymptote, what type of function am I working with? it's kind of like a rational function, right? At least that's the part that is really concerning to me. I notice that the numerator will be defined over its entire domain, even though that's a square root function. Why can I see that the numerator is defined over over all values of x? Because of the squared on the x, right? So I'm always going to get a positive number under that radical up there, so I don't have to worry about the numerator, even though it's under a square root symbol. The only part I have to care about is the denominator, and that's really only going to matter when it's equal to 0. Right? So if I want the limit as x approaches 5/3, now obviously I can't evaluate that, right? I can't direct substitute that. So what I'd want to do is think about it as coming from the left and to the right. If I pick something a little less than 5/3 and I substitute that in, I'm going to get a very, very small negative number in the denominator, but a positive number in the numerator. Everybody agree with that? That means that this is going to go to negative infinity. Everybody okay there? Since I have a very, very small negative number in the denominator, but just a regular old normal sized positive number in the numerator. Everybody's cool? Yeah. If I plug in something a little less than 5/3, I'm gonna get a negative number, right? 3 times 5, or 3 times that minus 5 is gonna be negative. But it's going to be really, really small because it's just a little less than 5/3. So you're going to end up with like a really, really small negative number, or a negative number really, really close to 0. Let me put it that way. That's maybe a little bit more clear. Okay? In the numerator, you're going to have like just some regular old big positive number in comparison, right? If you have positive divided by a negative value really close to 0, what are we sending that towards? Negative infinity, right? Because the negative number in the denominator makes it negative infinity. You could also do this by table. Like if you wanted to, you could do it by table. That would be okay. I just felt like it was going to be easier to talk our way through it. And then likewise, if we're coming from the right, when I do 3x minus 5, that number will be a very, very close to 0, but positive. So I have regular positive number on top, positive number close to 0 on bottom. That's going to give me positive infinity. Which again is what we needed to see to show a vertical asymptote. In fact, just one of these would be enough to get the vertical asymptote. You don't even need to do both. Mia. So that was to find a horizontal asymptote. So this piece that I did here with the verticals at the end is, yes, it's completely different than that previous example. But we did the same thing here with this example. I just didn't show any work. I just did it in my head, right? Which is ideally where we want to be able to go. We'd like to be able to do these limits at infinity just by looking at it without actually doing any algebra. So I would be multiplying by that, right? Mia?
Oh, so we just really complicated things.
No, I wanted to show you like this is strictly what the theorem is saying. And then here's like, it's always going to work the same way. We're just going to like look at the thing and do it.
What if the degrees?
So it can still work just fine.
Because if the degree is the same with the shortcut and the leading coefficients, or if it's different.
Depends on which one is the bigger. Depends on which degree is bigger.
Oh, if it's what?
If the degree of the numerator is less than the degree of the denominator, everything's going to work fine. It's just going to go to 0.
Okay.
Because when you do the same steps we did before, you can end up with 0 over something.
So if the degree of the numerator is smaller than the degree of the denominator, okay, what if it's the other way? It's undefined.
It'll go to an infinity, positive or negative.
Okay, so I'm guessing that's not going to happen.
Sure, that can happen. It just means there's no horizontal asymptote,
Oh, okay.
right? All right. So let's look at this thing. If I try to do this by direct substitution, what would I end up with? Like infinity minus infinity, right? Remember that that is one of the indeterminate forms, right? When I showed you guys this before, infinity minus infinity is one of our indeterminate forms. So that we can't do. So we have to go and figure out a different way to do this. What do you suppose we should do? What's going to be the trick here? Multiply by the conjugate. Excellent suggestion. X square roots don't distribute, sweetheart.
No, I know. But can't you just like square root that and just say it's like x minus 1?
Exponents don't how do you? It's not. That's
Yeah,
not x
never
squared
mind. Never
minus
mind.
1 quantity squared,
Never mind.
right? It's okay. You can ask these questions. And I can say, like, can ask disbelieving, like, questions back to you. That's okay, right? So far, so good. Whoa!
This thing scared me.
Look what happened. Look at that numerator. I know you're all awake from the fire drill, so.
Wow, that's a.
Wow.
That was like a compliment.
I know. Yes. Although it doesn't matter if I drop it. So, now if we look at this, Victoria, what's going on? What's the degree of the numerator? 0, because there's no x, is it? Degree of the denominator? 1. So what's this limit going to be?
0.
0.
Wow, I just it's like algebra 2, right? We did.
Mhm.
Wait, so numerator is smaller than
zero, denominator is smaller, it's infinite. There's
One or the other, positive or negative. Can't say without actually doing some analysis there. That's all right, right? That wasn't so bad.
Is this like, so it's 2.6, basically like horizontal asymptote and vertical asymptote?
Yeah, and these limits at infinity. Most of it is,
Oh, at infinity.
yeah, where we're having the x going to infinity or negative infinity or whatever.
Right, but we, so here we just found the horizontal asymptote. What about the vertical?
All the directions on this say is to compute the limit. So we're just practicing computing limits. Yes, that does mean it has a horizontal asymptote at x equals 0, for sure. And would this have a vertical asymptote? Yeah. You'd have to set that equal to 0 and try to solve for
The
it.
denominator,
Mhm.
so that's that, okay.
Mhm.
But when it's compute, we just wanna find the vertical,
Correct.
okay.
Oh. So this is just a proposition.
Oh,
The limit as x approaches negative infinity of e to the x is equal to 0, which hopefully should make sense, right? Since this should be the same as the limit as x approaches infinity of 1 over e to the x. Because if I put a negative in the exponent, it makes a reciprocal, right? And if I have 1 over something huge, what's that going to? 0, right? That's all. That's like my justification for it. Okay, what's up? If I have 1/2, that's 0.5. 1/3, 0.3. 1/4, 0.25. 1/5, 0.2. As the number in the denominator is getting bigger, you're getting closer and closer to 0. That's all we're saying. So like 1 over big is going to 0.
Okay, I just need to know that.
Correct.
yeah. That's like the same thing.
Yeah, that was my justification for why we can say that. Okay? Okay. Limit as x approaches infinity of x cubed. What should this be?
1. Oh, no, wait, I don't know. 0.
Positive infinity, right? If I get something huge and I cube it, still huge, right?
Right.
Oh. Yeah.
What if we do the other way? Go to negative infinity. Because it's 3 negatives. Yep, 3 negatives still make a negative. Yep. What's this going to be?
No, that's infinity, but
If you do direct substitution, you have infinity minus infinity. What's that?
0.
Nope.
No.
That's indeterminate. That means we have to do something else.
Oh boy.
I feel like we should combine it.
I love his like push-ups.
What if we write it this way? Right? Why is that helpful to me? Because I know the limit of a product is the product of its limits. So I have infinity times infinity, which is perfectly fine to just call that infinity.
For writing limit.
Not really.
In the form, I wrote limit of x prime.
Yeah.
Like 3,000.
Yes. Very good practice.
And towards the end of this talk, I was paying attention.
Look, I think if you have like that with a, if it looks like an L and you have the, I can tell what X is going to, I'm fine with it.
Infinity squared.
No, well, there's no such thing as infinity squared. Yep. Yes. Sure.
So for C that you just did,
Mhm.
you just been kind of passing out.
That's okay.
So you plugged in, like you substituted infinity into the first x, and then infinity into the second x, and then since it's x, or like infinity minus 1, that's still infinity, and then you multiply the two, that's just it.
Mhm. Correct.
I just need to talk that.
Yep. That's totally fine. Yep.
Makes sense, but I just will never know to do that.
But again, that's why we're doing the examples. That's why I'm showing you the examples, is to be like, when we get into indeterminate forms, you can't just do infinity minus infinity. What could you do? So I'm showing you like tricks so that when you run into this stuff, you have a trick. You're like, oh, maybe it'll be like this example. Maybe I can factor it some clever way to turn into a multiplication problem. All right. What's this going to be? Yes. Well, if we're not sure, let's do this.
Why don't you do that?
Wait, how are they?
Okay. Let's just like 3 people ask something all at the same time. That's okay, but it's when I hear them all at the same time, I'm not really sure what you want to be answering. So, why am I doing this? How do I know to do this? Because if I just tried to do direct substitution, what do I get? Infinity over infinity, right? You could do the degree stuff. That's exactly where we'd want to go. Should I be getting positive infinity or negative infinity? This is how I'm going to know, is by doing this. So I'm going to take the biggest degree in either the numerator or denominator and multiply by 1 over that. Okay, Sergio?
This is probably a stupid question. Could you just plug it in your calculator?
Assuming that you have a calculator active.
Okay. That's valid. Yeah, but like, you can't have it.
Oh my goodness. I don't want to do this. Why is this going to be a problem? I'm going to end up with 0 in the denominator, right? I just want 1 over x. I can't make a 0 denominator. Yeah, it's going to be the biggest one from the denominator. My apologies.
You just do.
I just made it 1 over x instead of 1 over x squared.
I feel so bad. Wait, why are you even doing one over x? What does that mean?
Great. So I started with the biggest one overall, right? And what I noticed is when I did that, I was going to end up, when I took the limit of the denominator, I'm going to get 0 in the denominator, and I know that's bad. That's an indeterminate form. So I was like, can't do that. The biggest I can take is 1 over x, because that'll still ensure that I have something left in my denominator. So that's why I went back and revised it to
I
that.
just feel like it's like 1, that didn't work. You did 1 over x. Is that what you said?
I had 1 over x squared initially.
Yeah.
When I did that, I was going to end up with a 0 denominator when I do the limit in this step.
Yeah, I just don't understand like where 1 over x or 1 over x squared comes from. Like that's just what it's just something you do.
So I'm just multiplying by 1 here, right, Victoria? Can you guys just give me a second, okay? I'm multiplying by 1, right? 1 over x divided by 1 over x is just multiplying by 1. Agreed?
I'm sorry.
Like when you make a common denominator.
Yes.
It's just like making a common denominator, correct?
Oh yeah.
Where I'm multiplying by 1. Okay. The reason I'm writing it as 1 over x over 1 over x is because I want to get all of the x's out of my denominator.
Oh, okay.
And the reason I want to do that,
Because there's only 1 x, so then it's 1 over x.
correct, the biggest degree, if there was an x squared in the denominator, I would use 1 over x squared.
It was like x cubed.
Then I would use 1 over x cubed. I'm just going to use trying to get all the x's out of my denominator. And when I say x's, I mean like x's in the numerator of the
Yeah.
of the fraction that's in the denominator.
No, I understand.
Yeah. Okay. So I did that, and then I split my limit to the numerator and denominator. If I take the limit in the denominator, the limit of 3 over x is 0, and the limit at -1 is just -1. Everybody agree? And then the limit in the numerator is infinity. So this should come down to -infinity. So all of that was just so I could figure out the sign of whether that was going to -infinity or +infinity. Because as you guys pointed out to me, you knew that it was going to be one or the other.
Oh yeah, I don't know how. Wait, Mr. Coolidge.
Yes.
How did you get up from 3 over x minus 1 to just be like negative or what?
The limit of, as something going to infinity, of x in the denominator is just going to 0. Right? This part, if I do the limit of that part, that's 0, right? Because you have 3 over big. That's 0. The limit of a constant is just a constant. So 0 minus 1 is -1. Yes, you got to avoid the indeterminate forms, right? If you run into an indeterminate form, it's like back to the drawing board, got to try something else. And again, those indeterminate forms, 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 0 to the 0, 1 to the infinity, and infinity to the 0. Those are your 6 indeterminate forms. Yeah. Okay. Did you send me an email to remind me to go back and check? And you guys are done. Like, you guys can go. I don't know. Thanks for staying.